Okay, problems. Here we go. First question. This is first question. Computer uses memory unit with 256k words or 32 bits each. Okay, a binary instruction code is stored in one word of memory. Fine. So memory unit 256 cross k. Okay, 256k cross what 32 bits. So basically like 56k is like 16 squared is 2 power 12. Wait, so 2 power 6 is no wait 2 power 4 is 16, so that power 2, so it's 2 power 8 times 2 power 10, so that's 2 power 18. So this is basically 2 power 18 cross 2 power 5. Find 5 bits and 2 power 18 of these. Right, binary instruction code is stored in one word of a memory. So for each word you will basically have some instruction in it. Cool, no big deal. The instruction has 4 parts: an indirect bit, an operation code, and a register code. Okay, indirect bit, some OP code, and then this is the address. Fine. Oh, okay, a register code to specify one of 64 registers. So inside your machine you have 64 registers and an address part. Fine. So it's okay, this is a register code and this remaining thing is the address part. So 64 registers require log base 2 of that, which is 2 power 6, so it's like 6 bits. Yeah, this is 6 bits. The instruction bit is obviously just 1. Then the address part, that is that's going to be 18 bits. And so then the code, so the operation code will be just how big was this. The thing is 32 bits, right? So 32 minus this stuff, which is 7, and then it's like 25. So this is going to be 7. Yes, that's the thing. So it's a 7-bit operation code. Fine. So first question is, how many bits are there in the operation code? 7. The register code part, this is 6, right? The address part 18. So combine them all. That's so it's like 14 and that's is that, yeah, that's 32. That is certainly 32. Fine. Okay. B is draw the instruction word format and indicate the number of bits in each part. Oh, come on, I just did this. Fine, I'm gonna do it again. So this is 32, right? So this is gonna be 31. This will be like 30 all the way till 30. So this is 7 of them. Yeah. Wait a second. Okay, that's 24. So that's gonna be 24 over there. Fine. Then this is 23 all the way till, so that's 18. And then finally 17 all the way to 0. So this is the register code. This is the address. This is the operation code. And this is the I value, as in the direct indirect thing. Yeah, indirect bit and all that. Fine. So just delete all of this. I guess actually don't delete this. This will come in handy. Delete all of this. And this is our answer for B. Let's go to C. So C is how many bits are there in the data and the address input of the memory? Data address inputs of the memory inputs. Oh, so you mean this memory block has some address, right? Okay, fine. And the data, what's the data? Oh, because from the bus you have to do this thing. So from the bus you can take 18 bits, sorry, 32 bits, because 2 power 5. So yeah, and the address, right? So that's got to be 18 bits, so that you can specify all of the words in the memory. Fine. Cool. Let's go to second question. Fine. Second question is, what is the difference between a direct and indirect address instruction? How many references to a memory are needed for each type of instruction to bring an operand to a processor register? So direct, indirect. The first basic difference is the pin, obviously. So indirect pin is 1 and here indirect pin is 0, right? Both of these are memory reference instructions. Cool. Right. address instruction. How many reference? So for the direct case, we just have so whatever is M array. So AR is just the reference, right? So that's our data register. Over here, this would be something like AR is this, and then after that, BR is this. I'm gonna put a semicolon. Yeah. So here, just one reference is needed. Here, two references are needed, or more like a reference to a reference is needed, basically. Yeah. So they wanted how many address references to memory are needed. So yeah, this is a reference to memory. So fine, cool. This is okay. For each type of instruction to bring an operand to the processor register. Yeah, okay, we got it. So this was easy. Next, third is the following control inputs are active in the bus system shown something specified. So they have given this diagram S2, S1, S0. So A, it's 111, 110, 100, 000, whatever. And the load of register. So load of register. So basically, like which register has its load pin on. Yeah. I don't know why there couldn't be multiple of them. I guess they just didn't want. Then you have this memory thing. I'm just drawing like whatever they have drawn in the question. So like you can see what's gonna happen. The memory. So in this is read, nothing, write, nothing, and then the adder. So I'm just gonna call that ALU. So what is the ALU doing? So it's not doing anything, not doing anything, not doing anything. It's adding. Fine. So I just basically like need to understand what these instructions mean. Like what would these be in the form that we want them to be in? Alright, so the shift, basically the register shifts. Let's see. So you got S1, so S2, S1, S0 is 111, that's 7. So the last register we're talking about, right? What is the last register? It's the IR thing, I think. So the out register takes stuff from the bus. So that can't be the thing. Temporary register, probably. Yes. Yeah, I guess that's the scenario. So the TR register is what 7 is referencing. Once again, I'm just gonna draw the thing. So you got the memory, then the address register, and the program counter, then the instruction register. No, wait, okay, that's not at the top. Fine. Program counter, the data register. Sorry. The accumulator. Yes. The input register. So the input register doesn't actually like connect to the bus, so let's not draw that. Fine. Then I think you have the input register. Yeah, so the instruction register, and then the temporary register. Yes. It's tempting to say that the temporary register should be closer to accumulator, but no, that's not the way it is somehow. Yeah, for some reason. But anyway, that's the way it is. So this is like 0, 1, 2, 3, 4, 5, 6. So when we say 111, we mean 7. 7 is not there, is there? Did I miss something? Let's see. Memory. Instruction register is there. The temporary register is also there. Data register. Must have missed something because it can't be like this. Output register is just connected to the, so it takes from the bus, it never like gives to the bus, right? Yes, so it's just impossible. How is it that I'm missing something? Wait, it's the memory, then it's the address register, yes, the program counter. I also have a temporary register at this point. The data register, instruction register, and then yeah, these are all the ones. Am I missing something? No, possibly not. Multiplexer, it can never reach 7, can it? I must be missing something. What is it that I'm missing? No, this doesn't make sense. The ALU is just... Wait, what? How is it that you have 7 over there? Or like, no, 7 is the correct number, right? Yeah. Yeah, so like 111, that's a wrong thing. You cannot... There is no register like that. This doesn't make sense. Wait, I'm just gonna look at the diagram again because I'm sure this is incorrect. Yeah, this doesn't make sense. Like, you cannot have a 7. It won't make sense, right? Where is the diagram? Where is the diagram? Let's see. So you have the AR, the PC, the DR, yes, the accumulator, then the instruction register, and then the... Yeah, that's the thing. So it is actually just... Huh? Yeah, there are exactly just 7 of these. Wait, what the... Yeah, so... Wait, what? Oh, okay, I think I messed up a little bit. Yeah, I get it. I didn't see the labeling. So yeah, okay, I messed up. So all this reading and I didn't see the labeling correctly. It's not right. This isn't S1. Yeah, it's not 000. It's instead 7 over there. So what does 000 refer to? Hey, I don't even know what this 000 would be. I gotta read. Where is it? Where is it? Okay, I don't see anything. Hey, so what happens when all of these are 0? Basic computer has... So I'm just gonna read the control bus system once again. So it says that the basic computer has 8 registers, memory unit, whatever, all that stuff. The outputs of 7 registers in memory are connected. Find the specific location that is selected for the bus lines at any given time is determined by the binary value of the register. Find the number of along which input shows the decimal equivalent. Find 16-bit outputs. So this is actually 7, 1, 2, 3, 4, 5, 6, by the way. The lines from the common bus are connected to the inputs, whatever the particular register whose load input is enabled. Fine. So there is no 0, unfortunately. What does that mean? What happens when it's going to be 0? Hey, so there's nothing... Wow, I was not expecting this. Yeah, that doesn't make sense at all. What the hell? Okay, so this is not in the thing. I just have to read actually. Like, what will happen if all of these are 0 though? Wait, what's S again? Oh, okay, I think I get it. I might just be getting it. So when S is 0, you just stop doing anything, as in your bus will not, do stuff. Oh, I see. Right. It makes sense. So when we say S is 0, wait, no, that can't be the case. Wait, what the hell? Yeah, okay, this doesn't make sense. Okay, I'll just search about this. Nano machine. The select. Okay, bus select inputs being 0, right? That's our issue. Yep, nothing about this. Wow, that's just excellent, isn't it? Yeah, I don't quite like this. Fine, let's just try to see how can we solve this question. Where did the problem go? Yeah, it was the third problem, right? Specify the register transfer that will. Okay. Uh, maybe the 000 case is something like, I don't know. Could it be that it's something like, you know, yeah, so you don't have anything being loaded onto the bus or something like that. That could be a possibility, right? Like whatever is on the bus, you just take that and I see. Yeah, could be a possibility. As in, there's no basically like nothing that is trying to output to the bus. Yeah, okay. If that were the case, in that case, this thing 000 AC, yeah, all that stuff, what it's doing is just that accumulator gets accumulator plus to get data register. Like, yeah, I mean that's kind of the only thing that it does. Uh, but that's about it. Like the bus does not communicate. Wait, no, okay. The load of the register accumulator is okay. The load of that being just means that accumulator is getting something. The data register is not having the load on, which means that it is not getting anything from the bus. So it's just this, like not caring about what the bus is doing. Fine, I guess that's okay to live with. Yeah. Fine, fine. Okay, let's just do the other ones. So S2, S1, S0 is 111. That's to say it's 7. So 7 is at the memory. So yeah. So it's instruction register is getting some stuff. We're saying read from the memory, and the ALU is not doing anything. So it's basically just this instruction. So whatever is AR's value, I mean AR is an input to N after all. Okay, what about this one? 110. 110 is 6 basically, so that's the temporary register. So temporary register is getting, oh sorry, that's the one that is that's being put on the bus. So it's just PC gets DR. Okay, over here the DR thing, it gets, so saying write. Okay, the ALU isn't doing anything. What are you inputting? So 100, that's 4. So the accumulator basically. So whatever is in the accumulator, just put that into the AR, into the DR thing. At the same time, also write that into the memory. The load for wait, that is weird. Oh, I see. So whenever you say write, it takes the stuff from the database. There's no load. There is no load basically. I get it. And so just have MAR being written as AC. Makes sense. So that's the third question. Yeah, I guess. Next, the fourth question. Fourth is, the following register transfers are to be executed in the system, okay, of figure 5.4. For each transfer, specify the binary value that must be applied to bus select inputs. The register so basically I have to create the table now. Fine. Oh damn. Okay, it's not fine. I just create the table. Cool. So you have the instruction. Not the instruction, I should just say the shift basically. Like register shift. Fine. We gotta create the thing. So yeah, the load of register something, the status of memory, whether you're reading or writing, the ALU's function, and the S1 and all that stuff. So S2, S1, S0. Cool. Let's just start. So first, it's A is AR gets PC. Fine. It's in the load of register AR obviously. program counter is at which location. I don't want to be drawing that again, but I have to at this point. So yeah, memory, AR, PC. Okay, so this is 712, so PC is at 2. Fine. I don't know about the memory, but this would be 2 basically. The memory isn't like doing anything, is it? Hey, why did I say 8? Oh, because it is AR. Okay, memory is not doing anything. The ALU is also not doing anything. Okay, the next is IR gets MAR. So the memory is supposed to be read from. So it's read. Okay. The load is for IR. This thing is just 0 because like you're not. Wait, what the? No. When you read. Wait, what the hell? Oh yeah, so you have to get it into the bus, otherwise it doesn't make sense. So it's gonna be 7. Fine. The ALU is not doing anything. Next is MAR gets TR. So TR is the last register, so it's gonna be 6 basically. ALU isn't doing anything. Memory is right at this point. Yes. The load is for. Well, the load is not actually doing anything because once this is right, you don't have to specify the load anymore. Yeah, I guess. Heck, I don't even know if this is correct. So it's when we say it's right, it really just means right into the memory, I think. Yes. Okay. Next, AC gets DC, and DR gets. So 2 operations done simultaneously. So the load of registers AC and DR will be on. Wait, what's DC? Oh, okay, that's DR, sorry. Sorry, yeah. Wait, how the hell are you going to do this simultaneously though? What the hell? Oh, I see. You don't swap because you have the accumulator. Makes sense. So okay. You can use the ALU to do the first operation. The other operation will be done with the bus. So just the load of DR should be on. Right. You're supposed to be writing from the accumulator. So the accumulator is so it's program counter. Then this is a direct register. Wait, I'm messing up something. So the instruction register not first. It's the DR thing which is the first, and then the accumulator. If I'm being correct. So this would be 4. Yeah, this doesn't do anything. So wait, what the hell? Yeah, so this operation is done by this thing in the ACs. So what is the ALU supposed to do? Like nothing essentially. Like it's just supposed to take whatever is in DR and put it to the. Yes. Oh wait, then the load of the accumulator should also be there, right? Because it has to accept it in the end. Yes. Okay. Wait, how do I write this? It doesn't do anything. So like, just like put it into DR. Like, what is it called? It's not load A. No, that's not the thing. Load A requires another thing. So this is certainly not the thing. Hey, what is this operation? I don't remember. I don't think I remember. Wait, I'm just gonna look at all the things that the ALU can do. Okay. Well, that's just the implementation for that thing. Where is the ALU? What can the ALU do? It can shift, it can do all that. So it's just transfer, essentially. Right, okay, so can the ALU just transfer? I just want to see what is possible. The arithmetic circuit, where is that? Yes, okay, there are a bunch of roadblocks. Fine, these are all the instructions and okay, it's not there. It's just not there. How come they didn't even write what the arithmetic circuit is supposed to do? Am I not supposed to know like what it is going to do? No, there is nothing about it. Okay, it doesn't make sense. But I'm just gonna call it transfer. Like ALU is like transferring basically. That's its role. Heck. Wow, there's everything about this, but there isn't anything about the ALU itself. Ah, bus. Okay. It's just called an adder and logic. Like nothing. Seriously. Come on, give me something about it. Oh, okay, okay. So there is something about it. Fine. So they have combined the LU and the accumulator somehow. Yeah. Okay, that's just one particular bit of the accumulator things. Fine. Okay, that's a shift operation. That's a shift left. COM operation. So it's actually called the DR operation apparently. Yeah. So you just fine. So I'm gonna call it just DR. As in, yeah. That's what the ALU is doing. It's just letting whatever is DR's bits into this thing. Okay, I think I should draw this figure out, but like I'll do that later. Yeah, okay. So the operations that the ALU can do, I'm just gonna list them out and add. So add the DR and accumulator thing. Obviously, it's using full adders and all that. Fine. The DR, which just shifts whatever is the DR's bit into it. The INPR thing, which just shifts whatever is the input register bits into it. The COM thing, which complements shift right and shift left. Okay, fine. Yeah, okay, I think I get it now. So that's what I'm supposed to write. Cool. So yeah, fourth is done. Cool. Alright, let's go to the next one. Just gonna copy it. Fine. Fifth is explain why each of the following micro operations cannot be executed during a single clock pulse in the system shown in figure 5.4. Why each of the following operations cannot be executed in a single clock pulse. Fine. Specify a sequence of micro operations that will perform the operation. So first operation is IR gets MPC. This is complete garbage. You cannot do it in a single go because the thing is PC is not connected to M. The only thing connected to M is AR, right? And so yeah, you have to first shift the contents of PC into AR and then do this thing. So this cannot be done. So like PC is not connected to M, obviously. B is AC gets AC plus TR. Once again, TR is not connected to AC. That's the main difficulty. So you could think, okay, just shift that to data register and then do the thing. Yeah, it doesn't work like that. In one clock cycle, whatever are the previous values of the registers, only those could be used. And so this cannot happen, essentially. Like you can only use the data register to combine with the accumulator in some sense. So once again, TR not connected to AC via ALU. Alright, C is DR gets DR plus AC. Once again, you cannot do this because okay, DR plus AC requires the ALU. So you can put that in AC, sure. Wait. This might actually be doable. AC does not change. Okay. This is different. This is extremely different because you are saying that this should happen at the same time. Accumulator should not change, so you would have to store it in some temporary register. But yeah, that obviously requires multiple cycles, right? So if AC is not to change, then you have to store it, because this will certainly change it. So storing that requires one clock cycle, and then retrieving it requires one clock cycle. Yeah. So storing needs one clock cycle. Retrieving needs one clock cycle. So once again, just so you know, this was the instruction. Retrieving needs one. Fine. That's fifth question. So the sixth question. Consider the instruction formats in the basic computer. Okay, fine. In the list of instructions given in table 5.2, for each of the following 16-bit instructions, give the equivalent 4-digit hexadecimal code and explain 4-digit hexadecimal code. Yeah, that should be easy. Explain what is the instruction going to perform. Fine. So just you have to comprehend the instruction. That's pretty much it. So first it's this thing 0001 0000 00100100. So the hexadecimal code for this would just be 1, 0, 2, and 4. Okay, cool. So what is it doing? Well, first thing is that this I bit is 0, so it's and also this D thing is actually like 1. So this is basically decoded as, I is 0, and then you just have D1 basically, right? And the remaining stuff is just the address. So this address is basically like 024. Yeah, so that's going to be the, after the fetch cycle, this will be the address value. So this is 024. So yeah, that's the thing. So what does this mean? The D not being 7 means we are doing some sort of memory instruction, right? So memory reference instruction, MRI. And I equal to 0 means it's a direct thing. So it's basically like direct. So what is 1? 1 is for add, obviously. So it's add 0 to 4. That's what this is essentially. And the I thing is 0, so it's like I'm just gonna call it 0 add 0 to 4. This basically like adds M0 to 4 to accumulator essentially. Yeah, I don't think we need this stuff right now. Okay, so that's A. Should probably, yeah, better. I'm just gonna write this thing. So this is basically like 0, the I, so yeah, add, and then 0 to 4 x adds and 0 to 4 to accumulator. That's what it does. Okay, cool. B is 1 0 1 1 0 0 0 1 0 0 1 0 0 1 0 0. This is a 1 over there. It's an indirect thing. The D thing is not, what do we call it? Heck, I forgot it. Okay, but what is this? It's 3, right? Okay, so it's 3, which is, I just write this, and add. Wow, I'm thinking, am I losing stuff? Load, obviously. Store. Branch operations. An ISZ operation, right? These are the ones. You got 1, 2, 3, 4, 5, 6, 7 of these, which is making sense because you just have 7 things, right? 0 till 7. Oh yeah, that's 8 operations. 0, 1, 2, 3, 4, 5, 6. Okay, wait, what? No, right, it's 7 because the last 1 1 1 thing is for the special kind of a thing, right? Yeah. So this is 3, this is 0 1 2 3. It's store, so it's store accumulator, indirect, this address, so just 1 2 4. So essentially what this is doing is, I'm just gonna write the thing out actually. So obviously, like, whatever M1024 is what AR is. So AR is just like M124. It's indirect reference to that, right? And so now what this is doing is, so I'm just gonna call it with this thing do, so you're just storing it, right? So it's just like MAR is what accumulator was. Cool, that's kind of the thing. Yeah, so essentially it's doing something like M1 to, do I even need to do this thing? So whatever is M124, it's a pointer to some address. At that address it's storing the accumulator. I'm not even going to explain this in words. Alright, C is 0 1 1 1. Okay, fine. So it's already 1 1 1, it's D7 and it's 0, which means it's a RRI operation. Alright, cool. So let's see, this thing is B11, B10, B9, 8, 7, 6. So it's B6 basically, right? Okay, let's just start writing down the RRI operations. I hate this stuff. But let's just do this thing. Clear A, it's called CLA actually. Clear E, complement A, complement E, circulate right, circulate left. What else? The increment thing and the skips. So skip on positive accumulator, skip negative accumulator, skip 0, skip 0E, and then the halt. These are the ones. So it's 11 10 9 8 7 6. So 6 is this thing, so it's circulate to the left. What are we doing? Just doing circulate to the left. Yeah, that's pretty much it. You don't need an address for this. So yeah, it's just that's the thing. It's that operation. So this thing is just circulate to the left. Fine, I guess. That's going to circulate to the right. Yeah. Increment 3 skips. Hey, wait, what? Did I mess up? Oh, I did mess up. Oh, wait. There's an extra 0. I didn't draw that. Yes, I messed up. I hate this. It's an extra 0 over there. So that's going to be B8. This is 7 6 5. So it's not circle to the left. Instead, it's increment. So it's actually like just the INR thing. Or INC. Yeah, that's the symbol for it. INR is the pin. INC is the operation. Fine. B. B8, right? This was 8. B7, B6, B5. Yes. This is. You just do a count and add. Shit, sorry, those are MRI operations. Yeah. Clear A, clear E, complement A, complement E. What was that? Circulate to the right, circulate to the left, increment. The 3 skips for A, the skip for E, and then the halt. Yeah. Fine. D. There's no D. Okay. Next. 7th. 7th is what are the 2 instructions needed in the basic computer in order to set the E flip-flop to 1. 2 instructions needed. What? The E flip-flop. So those are once again just RRI operations. So you have circulate to the left, circulate to the right, and all that stuff. Fine. You want it to be 1. What the? You complement E and all, right? Oh, okay, okay, wait. There is no, so other than the complementation, there was no other that sets E, right? No, there wasn't. But there was a skip statement. I see, we can use that. Okay, so which is gonna skip, um, that's not how we draw it. Skip on 0 E. So if E is 0, I see. Hey, that's not how it works, right? Wait, what the? It's supposed to be 2 instructions. In the basic computer tuning model set. Do you mean like, oh, so the 2 instruct, this is just wordplay. Do you mean like 2 instructions in the memory or 2 instructions? As in, like, instructions, like a type of instructions that you're gonna give. Because if it's the second one, then it's like doable. So I can write a program that will do this thing. So first we'll just skip if it's, if like, so if E is 0, then this line skips the next thing, right? Okay, so first if E is 1, you don't want to be doing anything. Right, I'm just gonna put another skip over there. So this just skips like unconditionally. Hey, wait, what? There's no unconditional skip, is there? No, there isn't. Shouldn't there be? What the hell? Okay, first let's just think about it. So say you have, say your E is 0, then you first complement it. So complement E. Now it's 1, right? Then I say that if your E is 0, then just skip the next part. Hey, what? That doesn't make sense. What did I do? Okay, so it's 1, so it won't skip the next part. So in the next part I have to do something that will, okay, wait, so if it was 1 initially, this would be 0 at this point, and so it would skip the next part. I'm just playing around with stuff, isn't that right? Oh, okay, I think I got it. So just think about it. If it was 1, so you skip and then you go to something else. If it was 0, no wait, if it was 0, you skip and you make it 1. If it was 1, you don't skip. I see. So you can just put in complement E over here and complement E over here. So when it's 1, so if E is 1 over here, that now it just like goes into this statement like without bothering. But now it's E0, then it's E1 again, and so it's still E1. If it's a 0, it skips to this statement, and so in that case it becomes 1, right? So just 2 statements are required, basically SZE and then complement E. Like the program would just be this thing. Eighth is draw a timing diagram similar to something some figure, assuming that SC is cleared to 0 at time t3 if the control signal is active. What? Control signal C7? I have no idea what C7 is. Figure 5-7, I'll have to see it. But once again, what's the question? Draw a timing diagram assuming that SC is cleared to 0 at time t3 if control signal C7 is active. Okay, so they have just given this statement essentially. No, I mean like they literally have given this statement and they just explain the statement. C7 is activated with a positive clock transition associated with T1. What? Okay, positive clock transition associated with T1 that triggers C7. Okay, so I'm just gonna imagine that T1 was like not doing much. Associated with, what do you mean clock transition associated with T1? Oh, okay, so the T1 thing must have been high over there, right? So at some point your T1 was, so this is your T1 was like this. This was your, so I'm just gonna draw it like slanted a bit or something. Then this was your clock transition, so it's just one of these pulses or something. I have no clue what I'm doing, but yeah, just hang around. Hopefully we'll figure out something. So this is your clock, and so this is a negative, sorry. I gotta do the opposite thing. This has to be positive. So it's supposed to be like this. Right, this is your clock. So this point is basically what is the transition associated with T1. And so at this point you should have C7 being high. So after this point your C7 is high. This is really bad. Okay, and then your T3 is something like, I don't know, maybe it was high from like the get-go or something like that. Like you gotta wait for another pausage. I'll have to draw another pausage. Right, so your C7 was high. I'll just make it a bit bigger, be like this, right? And this was your T3, I think. So let's say your T3 was also high all the way to this. Oh wait, it can't be. Once it's at T3, it's probably gotta go to some other stage. Because if it's not, it's stuck, which doesn't make any sense. You can only go back to T0, right? Okay, wait. Right, this doesn't make sense. Like T3 and T1 can't be high at the same time. It doesn't make any sense. So once this is off, you gotta go to this thing. This is T3 until the next pausage, where something else happens. It goes to some other state. No idea. But yeah, so actually we know which stage it goes to. It goes to T0 because SC is 0. Wow. Okay, they actually gave it away like directly. And so this becomes high until the next pausage. So that's how it's gonna be. And it's the 8th question. I'm not even going to like look what this really is supposed to be, but whatever. Next question. 9th. The content of EC in the basic computer is hexadecimal A937. Okay, so AC is this. Some content, fine. And the initial value of E is 1. Alright, determine the contents of AC, E, P, CA or whatever after execution of the clear CLA instruction. Repeat 11 more times. What? Starting from each one of the register reference instructions. Huh? Okay, so they are also given the initial value of PC. So PC is initially 0 to 1. Okay, hexadecimal. Wait, okay, what are they saying? We want the value of the stuff basically after this instruction, the CLA instruction. Then we want to repeat this same process 11 more times, starting from each one of the register reference. Oh my god, no, I don't want to be doing this. I see what you're trying to do. I don't like what you're trying to do. It's going to be painful. Fine, just do it. You also have some skip instructions, so that's going to be a pain. So just the instruction, okay, wow, fine, the instruction register, the program counter, before and after, right? Okay, so I'm just gonna, so like initially, and I'm just gonna say instruction and after the instruction has been executed. So whatever is the value after that, I'll just go with that, right? program counter, the E thing, the AC thing, and obviously the AR thing. Fine, just start it. So first you have instruction register is just, well, we kind of don't know. So some stuff we don't know. Fine. The program counter at least we do know. It's 0 to 1 hexadecimal. Yeah. The E thing is 1. AC is A937. The AR thing is, oh, by the way, this is actually 4-bit, so yeah. The AR thing is, once again, we don't know. So just, this is a 12-bit number, by the way. Alright, let's start. First, a clear A instruction. Oh no, wait, we'll have to draw the OP code for this. I don't want to. Fine, just do it. The instruction, we wanna draw the OP code for this as well. Alright, it's the OP code. I hate this. Okay, RRI operations, it's 0111, which means it's, in hexadecimal, that would be what? That would be 8. No, 7. So it's 7 and then some stuff. So CLA is just like, the first bit is there. So it's just F. Wait, not F. What would that be exactly? It would be, it's a 4-bit number. It's 8. It's 8, yes. So it's 8, 4, 2 and 1. That's the way it is. So it's 800. And you will have 7400 and 7300. Sorry, not 3, 7200. So 100, 7080. Yes, okay, so you now you see like why I didn't want to be doing this, right? But okay, once we get into the rhythm, this will be easy. Okay. So obviously the clear A instruction, the clear E instruction. Fine. So first we just have a clear A instruction. The program counter is this thing. Right. So what does it do? Oh, okay. I think I misinterpreted the question. What it was saying is that repeat the same experiment 11 times with the same initial values. But never mind, this is actually more interesting. Let's just do it that way. Yeah. So the program counter is 0 to 1, which is basically like wherever this OP code is stored. I shouldn't just call it OP code, it's the whole instruction. But like, never mind. I don't want to be putting this in the instruction register. But yeah. Let's just do the clear A instruction first. So how does the clear A instruction work? Well, A is cleared. So first let's start with the fetch. So the fetch means that whatever is in the program counter, which is supposed to be the next address basically, you put that into array, into the AR thing, right? Do you change the AR thing after that? Yes, you do. Wait, no, you don't, because yeah, you don't actually. What the hell? Hey, you actually don't. In the T3 itself, you just compute the whole thing, you don't change it. So then IR is just, the AR thing is just what was. I see. It's exactly the program counter contents, basically. So after this instruction is done, it will just be 0 to 1. Not the IR thing, sorry. The AR thing. It's just 0 to 1. Like, yeah, just, it is that. You're not using a memory block in any case. So this makes sense. Yeah, right. And the program counter will just be incremented. Pretty obvious. Remember, whenever you have a skip instruction, it will be incremented by twice, basically. So, yeah. Hey, wait. If it's incremented by 2, it will skip a bunch of instructions. It's kind of weird. Never mind. Uh, but first, you just have some instructions which are like completely logic and arithmetic. So it's just 0 to 3, 0 to 4. It's gonna keep doing that for a while. Okay, so we wanna complement A. Accumulator is this stuff. Complement that. Okay. What's the complement of A, 9, 3, and 7? For 7, the complement would just be 1, 0, 0, 0. So that's 8. Yes, it's 8. For 3, it's... What am I doing? Just what am I doing? I don't know what I'm doing. Yeah, it's like 2's comp. Okay, it's the subtraction thing, but with +1 or something like that. Fine, I'll just do it by hand. So this will be 1, 1, 0, which is just 8 plus 2, I guess. That's 10, which is A. 9, that is... That's 1, 0, 0, 1. Complement at 0, 1, 1, 0, which is 4 plus 2 is 6. So this will be 6 over there. Fine. And A is 10. So that's 8 plus 2. So it's 1, 0, 1, 0. Complement that's like 1, 0, 1. So that's 5. So this is this guy's complement. So you complement that just 5, 6, 8, and 8. E does not change. Right. You complement E after that, so it's now 0. It's still 5, 6, A, and 8. Yeah. Oh wait, once we start shifting it, it's gonna be a mayhem. I don't like this. Anyway, the AR thing, what is that going to be? Just the program counters contents. So far so good. What about the instruction register? I didn't like see anything on that. It's just whatever is the instruction itself, which is just this. So it's like 7, 8. Hey, what the hell? Oh yeah, this is this should be 7, 8, and so on. Okay, we don't have anything over here. 7, 8, 7, 4. So after this thing it becomes 7, 8, 0, 0, and then after this thing becomes 7, 4, 0, 0, and this becomes 7, 2, 0, 0, something. Yes, I'm not gonna continue this thing. 10. Okay, it's the same. It's saying instruction register address 0 to 1. The basic computer has... Wait, what? Okay, an instruction at address 0 to 1 has I equal to 0, an operation code of the AND instruction, and an address. So it's 0 and address part equal to 083. This instruction is stored at what? It's 0 to 1. Okay. Right, all numbers and decimals fine. Memory word at address 083. Oh, so 083 is somewhere over here. This thing contains the operand this number B8F2, fine, and the contents of accumulator right now is just this thing. So A937. Where's the program counter? Go over the instruction cycle, determine the contents of the following registers at the end of the execute phase. Where is the program counter? I'm just gonna assume the program counter is there. This is where the PC is. I mean, like, PC has this value basically. I think. Yeah. So what do you do? It's an add instruction, right? So after the execution, the AR thing just has this thing 08. It's like after execution. The AR thing just has 083, right? Yeah. The program counter just is like incremented, so 0 to 2. There is no skip or anything, so yeah, completely okay. The instruction register is just having this instruction. Yeah, because remember, it's in the first part that you feed the instruction register. After the execution, it's just that. So it's just this thing. Well, and is, hey, what's the OP code for? It's D0, so it's just 001. Okay, in hexadecimal, sorry. So this whole value is just 1. So it's 1083 in hexadecimal. So this part is in hexadecimal, this part is in binary, if that makes any sense. So just concatenate it or something. Fine. That's the instruction register's value. Then what else do you want? The accumulator, obviously. It's an add instruction. It just adds it. It just adds the so it's not an indirect thing, right? So it's just gonna add whatever is this content to it, right? I mean, since it's not indirect, that's why you have the 083. Yes, otherwise you would have like B8 F2 as a thing. What's the accumulator's value? It's just B8 F2 plus this guy 083 hexadecimal. I don't quite like this. Hey, wait, okay, no, that's the address, sorry. So it's B8F2 plus A. I don't know if I am capable of doing hexadecimal addition, but let's try it out. I don't have very high hopes from this. 9, F is what? F is 15, right? So 15 plus 3 is 18. 18 is 16 plus 2, so it's going to be remainder 2. 16 is 1 carried on. So it's 9 plus 9 is 18. 18 is 16 plus 2, so 2, 1, 10. Hey, is that correct? Wait a second. Yeah, it is correct. So that's B and B, which is 22. 22 is 18 plus 4. So this will be the value. Well, clearly the accumulator cannot hold something like that. So what's going to happen? Well, this is an overflow. Just delete that essentially, right? I guess so. I'm wondering if this is even correct. These are pretty big numbers. Oh, these are negative numbers, aren't they? Oh, it's an overflow. Yeah, it is an overflow. Damn. I was not expecting this. Wait, what do you do in overflows like this? It's still supposed to be a negative number. Well, I mean, I probably just should say it's an overflow. Yeah, I mean, it's an add instruction and it's... What the hell? I have no clue. I'm just gonna say it's just this thing. So it's 4229 after this is over. In hexadecimal, obviously. Okay. What else? The instruction register is done. Okay, the data register. Fine. So like whatever is the MAR thing, that's what put into the data register, right? For the add operation. So it's just gonna be that. It's just gonna be this B8F2 hexadecimal. What else? PCAR. The program counter is done, the AR thing is done, the IR thing is done. I think, yeah, this is pretty much done. So they want us to repeat this for all instructions. I am not gonna do that. Alright, that was the 10th question. Let's go to the 11th one. 11th is show the contents. I am sick of these questions. Okay, the 11th is also just the same thing. Contents are given of AC, program counter is given, the contents of memory address 3AF is, so the instruction is 9, 3, 2 and 1. A 9 just means, it means 8 plus 1, so it's an indirect one, and it's still an add basically. It's an AND. So before it was a direct one, now it's an indirect one. Big deal. Okay, they have given us the program counter initially is 3AF. The contents of memory address at 3 also, basically M3AF, that is 932E. Okay, the accumulator value, that's 7EC. Wow, this is just really bad. They want me to do so much of arithmetic. The unit of memory at address 32E is this. Okay, 32E is 09AC. Content of, okay, fine. I mean, it's an indirect address in the end, so you gotta do that thing. It's 9AC is 8B9F. So this is going to be the real deal. This is the number that you're going to add to the accumulator. So what is the instruction that will be fetched and executed next? What? You mean after the execution of this? The next thing? You mean during this cycle when the program counter is 3F, right? Well, if that's the case, then because yeah, we do not know what the instruction is. Like, we have no idea what is at 3B0. So how would we know? But okay. So the instruction is basically the memory of 3AF. That's just 932E. And so 9 is basically 1001, and then just have some address 32E. This is in hexadecimal. And so it's just an indirect addition with this address. So that's the instruction that's being executed. Alright, show the binary operation that will be performed in the AC when the instruction is executed. It's just an addition. What do you mean that will be performed in the accumulator when the when the instruction is this what do you want me to do exactly? Never mind that. So this was part A. Part B, I don't know, and I can't comprehend what they're saying. Give the contents of registers in the come on. Seriously. Just seriously. Okay, I'm not gonna do that. 13th is sick and tired of these sort of questions. Assume that the first 6 memory reference instructions in the basic computer listed in table 5.4 are to be exchanged to the instruction specified in the following table. EA is the effective address that resides in AR during the time T4. Okay, that's some bizarre thing going on. These are getting bigger and bigger as oh, there is like 25 questions. I don't think I'll be able to do it in another hour. Okay, I think we should stop here. So I'll see you guys next video. Bye.